So far we have been talking about functions that are complete, meaning the output column has a 0 or a 1. But sometimes you may not have incomplete functions, which means that sometimes you may not care what the output is. So for example, if you look at, say you're trying to do a elevator controller, right? So suppose you're trying to design an elevator controller for a building that has, say, 40 floors. So if the building has 40 floors, you might need bits to encode each of the floors. So how many bits do you need for identifying each floor? How many bits? How many bits do you need to identify each floor? Six is absolutely right, because 2 raised to 5 you reach 32, 2 raised to 6 you reach 64. So 40 is between them, so you would need 6 bits at least to identify each of the 40 floors in the building. Now, when you have 6 bits to identify these floors, you obviously have 24 combinations that are going unused. And here, the user doesn't care for these 24 combinations. So you're not going to write that as a 1 or a 0 in the output of the truth table. You are actually going to use X, the letter X, to indicate don't care situations. So these are literally called don't cares. And these are outputs that are associated with inputs that can be ignored. For example, the 24 combinations for the 40 floor building. And these inputs cannot happen in a good design, right? So that is why everywhere you will see things as a power of 2, so that you effectively use the number of bits. Elevator is just a real world example. I'm talking about applications in which digital design is involved. Now you are going to assign logic values to the outputs to simplify circuits. We can leverage don't care situations to simplify circuits a lot, and we'll see that in K-maps. That's very good to hear. Now let's take a look at an example of don't care outputs. BCD incremented by 1. This is a truth table of BCD numbers, binary coded decimal numbers. Of course, because these are binary coded decimal, you only have 10 valid symbols for decimal numbers, 0 through 9. So in binary, they are coded as 0, 1, 2, so on up to 9. But with 4 bits, you can have 16 combinations. So what happens to 1010? What happens to 1011? Those are all don't care conditions marked as X, the letter X in the truth table. So what I'm saying is, in the truth tables, you will now start seeing 0 and 1 and also X. Now let's try to do a very quick example here, which talks about a function Q which has a few don't care situations, and we are trying to write the canonical sum of product as well as the canonical product of sum expression for Q. So let's write it for CSOP first. Let's do it in black. So what should I write for CSOP? In the complete form, how can I write it? Actually, let's make it easier. How can I write it in shorthand instead of writing it in long form? Let's just write it in shorthand. So let me write it in shorthand here. I would say summation, right, because it's SOP. Then I would talk about the order of the inputs. The order of the inputs is M, comma, N, comma, P. Then I would talk about the row numbers where things are 1. So that would be 1 and 0, 1, 2, 3. But I cannot forget the don't care situations. So what I'm going to say is plus don't care situations at 4, 6, and 7. So those 3 go here, and those 2 go here. Next, let's talk about CPOS in shorthand. So over here, let's use blue. You are going to have a pi for product of sum. You are going to talk about the order of the inputs, M and P. Then you are going to talk about row numbers that are zeros. So you have got 3 of them, 0, 2, and 5. There's also don't cares. I need to include don't cares at both places. Why do I need to include don't cares at both places? Because you don't care. It could be a 1, it could be a 0. So I have to include it both in CSOP form as well as in CPOS form. So literally, what does don't care mean? It means it could be a 0, it could be a 1. All right, so I hope that this was why CP also addition. So the addition is just for don't care terms, and that's how they write it. So it's a standard notation thing. Does the order matter? Like, can I write D1, 2, 3? What do you mean? 1, 2, 3? Huh? I'm not sure if I understand. Why would you write 1, 2, 3? There's a 1 there, there's a 0 there, there's a 1 there. Change X to the first 3 places. Change X to the first 3 places. If you change the first 3 places, then it will be 0, 1, 2. Is the don't care term D, 4, 6, 7 inside the summation? Yes. So all of this is kind of there, and so here, as opposed to like how you literally write mathematical forms, this is slightly different. This is writing things in shorthand, and you cannot treat them the same way as you write arithmetic summation and product. So the summation is for 1 and 3, plus this function has certain don't care situations. This product sign for 0, 2, 5, plus this function has certain don't care situations. Where the don't cares go? How do you know where the don't cares go? Right now, I have just chosen an arbitrary truth table. But in this example, because we had a particular situation, that's how we knew the don't cares go there. Right, so that has to be determined by the problem statement, or a few statements that denote what that digital design is about. For example, here, right, the BCD numbers are only from 0 through 9. 10 to 15, hence, are don't cares with a 4-bit combination. Alright, so that is done, this is done. Okay, so now we can stop recording again.